The question of whether we are alone in the universe is not new. Humans have been looking up at the night sky for as long as there have been humans at all. Long before telescopes, before science, before written language, people noticed the quiet presence of the stars and wondered if something, somewhere, might be looking back. Tonight, we will take our time with that question. We won't rush to answers, and we won't repeat ideas simply because they are familiar. Instead, we'll move slowly through what we already know, what we quietly suspect, and what remains open and unresolved. In the moments ahead, we will talk about distant worlds that have already been discovered, planets orbiting stars far beyond our own, some of them strange, some of them surprisingly calm. We will spend time with the silence of the universe and consider what that silence might mean, without treating it as something frightening or mysterious. We will gently revisit what scientists mean when they talk about life, not as something dramatic, but as a simple process that unfolds under certain conditions. And later, we will reflect on time, distance, and the idea that the universe may simply be patient in ways that are difficult for us to imagine. You don't need to remember any of this. You don't need to follow every idea closely. If your attention drifts in and out, that is perfectly fine. Just let the thoughts come and go as you listen. For a long time, the question, "Are we alone?" belonged more to philosophy than to science. It lived in myths, stories, and imagination. But in recent decades, something has quietly changed. One of the most important shifts came when we realized that planets are not rare. For most of human history, we had no direct evidence that planets existed beyond our solar system. We assumed they might be out there, but we could not confirm it. Now we know better. Today, thousands of planets have been detected orbiting other stars. These worlds are called exoplanets, and their existence has changed how we think about the universe. Some of them are large and hot, orbiting very close to their stars. Others are small and cold, drifting far from any warmth. Some move in calm, stable paths. Others follow stretched, irregular orbits that would feel chaotic to us. What is striking is not just that these planets exist, but that many of them do not resemble anything in our own solar system. Nature seems comfortable creating worlds in many different forms. This diversity suggests that the universe does not follow a single blueprint. Instead, it experiments slowly and quietly over billions of years. As we discovered more of these distant worlds, another realization followed. If planets are common, then the conditions for life might also be more widespread than we once thought. Not guaranteed, not inevitable, but possible in many places at once. And yet, despite all of this, the universe remains silent. We do not hear signals. We do not see clear signs of distant civilizations. The sky, when observed closely, offers no obvious answers. This contrast between possibility and silence has become one of the most interesting features of modern astronomy. The universe appears vast and full of opportunity, and at the same time, deeply quiet. This silence is not necessarily a mystery that demands an urgent solution. It may simply be a fact of scale. Distances between stars are enormous. Distances between galaxies are even greater. Communication across such expanses would require time spans far longer than a human lifetime, or even the lifetime of a civilization. Before we go further, it helps to pause and consider something simple. When scientists talk about life, they are not necessarily talking about beings that think, communicate, or build technology. Most life on Earth does none of those things. For most of our planet's history, life existed only in simple forms. Single-celled organisms lived in oceans, underground, and in environments that would seem hostile to us. They did not wonder about the universe. They simply persisted. This is important because when we ask whether we are alone, we are often imagining something very specific. We imagine intelligence, technology, language, or culture. But from a scientific perspective, life does not begin with those traits. It begins with chemistry. Life, in its simplest form, is a process. It is a way for matter to organize itself, to maintain structure, and to reproduce under the right conditions. Those conditions are not magical, but they are precise. Water, for example, plays a crucial role, not because water is rare, but because it is a remarkable solvent. It allows molecules to move, interact, and combine in ways that support complex chemistry. Energy is also necessary, whether it comes from a star, from chemical reactions, or from heat within a planet itself. And time is essential. Life does not appear instantly. It unfolds slowly, sometimes over billions of years. What makes this comforting rather than unsettling is that none of these requirements demand perfection. They require stability, not intensity, balance, not extremes. As we continue, we will return to these ideas again from different angles. We will look at distant planets not as potential homes for civilizations, but as environments where simple processes might quietly unfold. We will consider silence not as absence, but as distance, scale, and timing. And we will allow uncertainty to remain exactly where it belongs. For now, it is enough to know that the question of whether we are alone is no longer asked in the dark. It is asked with instruments, with data, and with patience. The universe does not respond quickly. It does not reveal itself all at once, but it does offer small clues scattered across space and time. As we move forward, we will begin by looking more closely at the worlds we have already found. Not imagined worlds, but real ones, orbiting real stars, quietly moving through the vastness of space. And we will do so slowly. When scientists talk about exoplanets, they are referring to planets that orbit stars other than our Sun. Although this idea seems natural today, it was considered speculative for most of modern history. Only in the last few decades did technology become precise enough to confirm that such worlds truly exist. As of today, thousands of exoplanets have been confirmed. Based on statistical analysis, astronomers now believe that planets are more common than stars themselves. Most stars in our galaxy are likely accompanied by at least one planet, and many host entire systems. One of the earliest surprises was the discovery of gas giant planets orbiting extremely close to their stars. These planets, known as hot Jupiters, are similar in mass to Jupiter but can orbit their stars in just a few days. Surface temperatures on these worlds can exceed 1,000 degrees Celsius, making them inhospitable by any familiar standard. The existence of hot Jupiters forced scientists to revise earlier theories of planetary formation. Originally, it was thought that gas giants could only form far from their stars, where temperatures are low. Their presence close to stars suggests that planets can migrate inward over time, reshaping entire planetary systems. Another important discovery was the abundance of planets larger than Earth but smaller than Neptune. These planets are often referred to as super-Earths. They are among the most common types of planets detected in the galaxy, yet none exist in our own solar system. Super-Earths can vary greatly in composition. Some are likely rocky, with dense surfaces and strong gravity. Others may possess thick atmospheres or deep layers of ice and water. Their diversity suggests that size alone does not determine habitability. Closely related are mini-Neptunes, planets slightly larger than super-Earths but surrounded by thick gaseous envelopes. These atmospheres often consist of hydrogen and helium, creating extreme pressure conditions at lower layers. Such environments would be very different from Earth, even if temperatures were moderate. Another striking feature of many exoplanetary systems is how compact they are. In some systems, Several planets orbit their star at distances much smaller than Mercury's orbit around the Sun. Despite their proximity, these planets can remain in stable orbits for billions of years. This finding changed how scientists think about orbital stability. It showed that planetary systems can be arranged in configurations far more varied than previously assumed, without becoming chaotic. The type of star also plays a major role in shaping its planets. Smaller stars, known as red dwarfs, make up the majority of stars in the galaxy. They are cooler and dimmer than the Sun, which places their habitable zones much closer in. Because red dwarf stars burn their fuel slowly, they can remain stable for trillions of years. This extended lifespan could, in theory, provide long periods during which life might develop on nearby planets. However, red dwarfs also present challenges. Many produce frequent stellar flares that release intense radiation. Planets orbiting close to such stars may lose their atmospheres over time or experience harsh surface conditions. Some exoplanets are believed to be water-rich worlds. These planets may contain vast global oceans, sometimes hundreds of kilometers deep. While water is essential for life as we know it, such planets may lack land-based geological cycles that help regulate climate on Earth. Astronomers have also identified planets with highly unusual orbits. Some follow elongated paths, moving between extreme heat and cold over the course of a single year. Others orbit in tilted planes or even move backward relative to their star's rotation. These findings reveal that planetary systems are shaped by complex gravitational interactions. Collisions, migrations, and resonances all play a role in determining a planet's final orbit. What becomes clear from studying exoplanets is that Earth represents only one outcome among many. The universe does not favor a single design. Instead, it produces planets across a wide range of sizes, compositions, and environments. This realization shifts the search for life away from looking for exact copies of our home. It encourages scientists to consider many possible ways life might arise and persist under unfamiliar conditions. In the next part of this exploration, we will look more closely at exoplanet atmospheres. We will examine how scientists attempt to detect chemical signatures, what those signatures can and cannot tell us, and why certainty remains difficult. For now, it is enough to understand that the universe is filled with worlds of remarkable variety. They are real, measurable, and quietly orbiting their stars, whether or not they ever host life. After discovering thousands of exoplanets, scientists naturally began asking a deeper question, not only where these planets are, but what they are like. To approach this, they turned their attention to something especially difficult to study from great distances: planetary atmospheres. An atmosphere can reveal a great deal about a planet. It can tell us about surface temperature, pressure, and chemical activity. In some cases, it may also hint at processes that resemble those associated with life on Earth. Studying an exoplanet's atmosphere is challenging because the signals involved are extremely faint. Most planets cannot be seen directly. Instead, scientists analyze how starlight changes as it passes through a planet's atmosphere during a transit. When light filters through an atmosphere, certain wavelengths are absorbed by specific molecules. Each molecule leaves a characteristic pattern in the light spectrum. By identifying these patterns, astronomers can infer the presence of gases such as water vapor, carbon dioxide, methane, or oxygen. Water vapor has now been detected in the atmospheres of several exoplanets. This does not mean these planets are habitable, but it does confirm that water, a key ingredient for life, is present beyond our solar system. Carbon dioxide is also commonly detected. On Earth, carbon dioxide plays an important role in regulating temperature through the greenhouse effect. On other planets, Its presence may indicate volcanic activity or atmospheric stability. Methane is a more complicated case. On Earth, methane is produced by both biological and non-biological processes. In exoplanet atmospheres, detecting methane alone is not enough to suggest life. However, when methane appears alongside other gases that should normally react and disappear, it becomes more interesting. Oxygen is often discussed as a potential biosignature. On Earth, large amounts of oxygen exist in the atmosphere because of photosynthetic life. But oxygen can also be produced through non-biological processes, such as the breakdown of water molecules by stellar radiation. For this reason, scientists focus less on individual gases and more on combinations. An atmosphere that contains gases in chemical imbalance may suggest an ongoing process that replenishes them. Life is one possible explanation, but not the only one. Another important factor is atmospheric retention. A planet must be massive enough to hold on to its atmosphere over long periods of time. Small planets may lose their atmospheres due to stellar winds or radiation, especially if they orbit close to active stars. Magnetic fields also play a role. On Earth, the magnetic field helps protect the atmosphere from solar radiation. Whether many exoplanets possess similar protective fields remains unknown. Temperature is equally critical. Some planets experience extreme heat due to close proximity to their stars. Others are locked in deep cold. Even within the habitable zone, temperature variations can be large depending on atmospheric composition and cloud cover. Clouds themselves complicate atmospheric studies. They can obscure deeper layers and mask chemical signatures. This makes interpreting data difficult and introduces uncertainty into many conclusions. Despite these challenges, progress continues. Space telescopes, such as the James Webb Space Telescope, are designed to study exoplanet atmospheres in greater detail. They can detect fainter signals and observe smaller planets than previous instruments. With improved observations, scientists hope to identify planets with atmospheres similar to Earth's in structure, even if not identical in composition. Such discoveries would not confirm life, but they would narrow the range of possibilities. Another limitation lies in time. Atmospheres evolve. A planet that appears inhospitable today may have been suitable for life in the past, or vice versa. Our observations capture only brief moments in long planetary histories. There is also the question of false positives. Certain chemical signatures can mimic those produced by life without any biological involvement. Disentangling these effects requires careful modeling and repeated observation. Because of these uncertainties, scientists approach claims of life beyond Earth with caution. Extraordinary conclusions require strong and consistent evidence. So far, no exoplanet has met that standard. What exoplanet atmosphere research has shown is not that life is common, but that planets are chemically active and diverse. They are shaped by their stars, their formation histories, and their internal processes. This diversity suggests that life, if it arises, may do so in many different ways. Some forms may be familiar. Others may operate under conditions very different from those on Earth. As technology advances, future missions may be able to study exoplanets more directly. They may detect seasonal changes, surface features, or long-term atmospheric trends. Each of these would add another piece to the larger puzzle. For now, the search for life through exoplanet atmospheres remains cautious and methodical. It progresses slowly, guided by data rather than expectation. The absence of clear biosignatures does not mean the universe is lifeless. It simply means that life, if it exists elsewhere, does not reveal itself easily. This understanding prepares us for the next step in our exploration. If planets are common and atmospheres are diverse, why does the universe remain so quiet? That question leads us naturally toward the silence itself and the many ways it can be understood. When scientists discuss the silence of the universe, they are not referring to a poetic idea. They are describing a measurable absence of evidence, observed despite decades of increasingly sensitive searches. Given what we know today, this silence is not trivial. Our galaxy alone contains more than 100 billion stars. Current estimates suggest that a large fraction of those stars host planets. Many of those planets are rocky, and a significant number may orbit within habitable zones. If even a very small percentage of these worlds developed life, and an even smaller percentage developed intelligent life, the galaxy should not feel empty. This contradiction was first articulated clearly in the mid-20th century and is now known as the Fermi Paradox. The paradox is simple in structure. If intelligent life is likely, where is everyone? The paradox does not claim that life must exist elsewhere. It highlights a mismatch between probability and observation. To understand this mismatch, scientists first consider the timescales involved. The universe is approximately 13.8 billion years old. Earth formed about 4.5 billion years ago. Complex life appeared relatively late in Earth's history, and technological civilization only in the last few thousand years. This suggests that intelligent life may require a long sequence of unlikely steps. Even if life begins easily, intelligence may not. Another important factor is duration. Technological civilizations may not last long on cosmic timescales. If a civilization survives for only a few thousand or even a few million years, the chance of overlapping with another civilization is small. Distance also matters. The Milky Way is about 100,000 light-years across. Even traveling at a significant fraction of the speed of light, crossing the galaxy would take tens of thousands of years. Communication over such distances would involve long delays and signal degradation. Scientists have conducted systematic searches for artificial signals for decades. Projects such as SETI have scanned large portions of the sky, listening for narrowband radio signals that do not resemble natural sources. So far, no confirmed signals of extraterrestrial origin have been detected. This does not mean that no signals exist. It means that none have been detected within the limits of our search methods. Those limits are significant. We have searched only a small fraction of possible frequencies. We have monitored only a brief window of cosmic time. We have focused primarily on communication methods similar to our own. Advanced civilizations may not use radio waves at all. They may communicate using technologies we have not yet developed or even imagined. They may also have no interest in broadcasting their presence. Another factor is energy usage. Highly advanced civilizations may become more efficient over time. Rather than producing strong, wasteful signals, they may minimize energy loss. From a distance, such civilizations could be almost invisible. There is also the possibility that technological intelligence is rare by nature. On Earth, life existed for billions of years before developing complex multicellular organisms. Intelligence capable of technology appeared only once, as far as we know. This suggests that intelligence may not be a common outcome of evolution. It may depend on very specific environmental pressures and historical contingencies. Scientists also consider the role of planetary stability. Large impacts, climate instability, or nearby stellar explosions can reset biological progress. Many planets may experience frequent disruptions that prevent long-term development. Another concept often discussed is the idea of self-limiting civilizations. Technological species may alter their environments in ways that reduce their own longevity. This does not require catastrophe, only gradual imbalance. From this perspective, the silence of the universe may not be surprising. It may reflect how difficult it is for life to persist long enough, remain stable enough, and become detectable enough at the same time. Importantly, none of these explanations require pessimism. They do not imply that life is meaningless or doomed. They simply highlight the complexity of the processes involved. What the silence tells us, above all, is that the universe does not advertise itself. Information travels slowly. Signals fade. Civilizations, if they arise, may leave only faint traces. In the next part, we will explore more specific hypotheses that attempt to explain the silence in greater detail. These include ideas about thresholds, filters, and the possibility that some stages of development are far more difficult than others. For now, it is enough to recognize that silence is not emptiness. It is data. To explore the silence of the universe more deeply, scientists have proposed several structured explanations. These are not stories or speculations in the casual sense. They are frameworks designed to organize what we know, what we observe, and what we do not see. One of the most influential ideas is known as the Great Filter Hypothesis. This hypothesis suggests that somewhere between the formation of planets and the emergence of advanced civilizations, there exists a step that is extremely difficult to pass. The Great Filter does not specify what this step is. It simply states that one or more stages in the development of life are so unlikely that very few civilizations ever move beyond them. These stages can be divided broadly into biological and technological phases. The biological phase includes the origin of life itself, the development of complex cells, and the emergence of multicellular organisms. The technological phase includes intelligence, tool use, industrialization, and long-term sustainability. One possibility is that the Great Filter lies very early. Life itself may be extraordinarily rare. Even if planets with suitable conditions are common, the transition from chemistry to biology may occur only under extremely specific circumstances. On Earth, life appeared relatively quickly after conditions stabilized. This could suggest that life is easy to start. However, it could also mean that Earth was unusually lucky. Another possibility is that simple life is common, but complex life is rare. For nearly 3 billion years, life on Earth consisted only of single-celled organisms. The transition to complex cells happened only once, as far as we know. Complex cells require internal structures that manage energy efficiently. Without this, large and specialized organisms may not be possible. If this step is rare, then most life in the universe may remain microscopic. A third possibility is that intelligence itself is the filter. Many organisms on Earth are complex, yet only one species developed advanced technology. Intelligence may not provide a strong evolutionary advantage in most environments. Even when intelligence arises, technological civilization may face additional challenges. Industrial activity can destabilize climates. Resource consumption can create long-term pressures. Social and biological risks may accumulate faster than solutions. Another hypothesis focuses on time rather than rarity. Civilizations may exist, but not at the same time as us. The universe is vast in age. A civilization that rose and fell 1,000,000 years ago would leave little detectable evidence today. This idea is known as the temporal separation hypothesis. It suggests that intelligent life may be scattered across time rather than space. Overlap between civilizations may be extremely rare. There is also the question of detectability. A civilization may exist, but choose not to communicate. It may focus inward rather than outward. It may use communication methods that produce little detectable leakage. On Earth, our own communication methods are changing. We are moving toward fiber optics, targeted transmissions, and low-power signals. Over time, our technological footprint in space may actually decrease. Some researchers consider the possibility that advanced civilizations deliberately avoid detection. This is sometimes called the quiet universe hypothesis. The motivation could be caution rather than fear. Another explanation involves physical constraints. Interstellar travel may be far more difficult than imagined. Energy requirements, radiation exposure, and time delays may limit expansion. Even self-replicating probes, often discussed in theory, face challenges. They require long-term reliability and precise control. Small errors could accumulate over thousands of generations. There is also the idea that intelligence often turns inward. Rather than expanding across space, advanced civilizations may focus on virtual environments, optimization, or internal development. From the outside, such civilizations would appear silent. Some hypotheses suggest that we may not recognize evidence even if it exists. Our instruments are designed to detect familiar patterns. Unfamiliar technologies may leave signatures we do not know how to identify. Astronomy has already shown that nature can produce signals that once seemed artificial. Pulsars, for example, were initially nicknamed little green men because of their regular pulses. They turned out to be natural phenomena. This reminds us that interpretation is difficult. Absence of evidence is not evidence of absence, but it does shape how we reason. Taken together, these explanations suggest that the silence of the universe does not point to a single answer. It reflects a combination of rarity, timing, limitation, and perspective. Importantly, none of these ideas imply that humanity is unique in a cosmic sense. They simply suggest that the conditions required for long-lasting, detectable civilizations may be narrow. The silence may also be temporary. As our technology improves, we may detect weaker signals or subtler patterns. Future instruments may reveal phenomena that current ones cannot. For now, the silence encourages patience rather than conclusions. It invites careful observation instead of speculation. In the broader context of the universe, silence is not emptiness. It is a boundary of our current understanding. And beyond that boundary, possibilities remain. When we think about life elsewhere in the universe, it is natural to imagine it existing at the same time as us. This assumption feels intuitive, but it may be one of the largest obstacles to understanding the silence of the universe. Time in the cosmos operates on scales that are difficult to grasp. Human history spans a few thousand years. Modern technology has existed for less than 2 centuries. By contrast, the universe is nearly 14 billion years old. Even Earth's own history shows how brief our presence is. Life appeared on this planet more than 3 billion years ago. For most of that time, it consisted only of simple, single-celled organisms. Complex life emerged relatively late, and technological civilization appeared only in the last fraction of a second on a cosmic clock. This suggests that intelligence and technology are not inevitable outcomes of life. They may be temporary phases rather than permanent states. When scientists consider extraterrestrial civilizations, they must account for this imbalance in time. 2 civilizations could exist in the same galaxy, yet never overlap. One could rise, develop technology, and disappear millions of years before the other ever emerges. From a cosmic perspective, this would not be unusual. Stars are born, evolve, and die over billions of years. Planetary environments change slowly, sometimes violently, and often unpredictably. Life must adapt to these changes, and not all adaptations lead to long-term stability. If technological civilizations tend to be short-lived, even by optimistic estimates, the chance of 2 existing at the same time becomes small. This is especially true when combined with the vast distances between stars. This creates a kind of temporal isolation. Civilizations may be separated not only by space, but by time. Another important factor is the pace of technological change. On Earth, our communication methods have changed rapidly. Early radio transmissions were powerful and inefficient, leaking energy into space. Modern communication systems are increasingly efficient, directional, and quiet. This suggests that the window during which a civilization is easily detectable may be narrow. Before technology develops, there is nothing to detect. After it matures, there may again be little to observe from a distance. In this sense, technological civilizations may pass through a brief, detectable phase. If that phase lasts only a few centuries or millennia, the odds of overlap drop even further. Time also affects how we interpret signals. Any signal we receive today was sent in the past. The farther away the source, the older the information. A civilization detected at a distance of 1,000 light-years would be observed as it existed 1,000 years ago. By the time we receive such a signal, the civilization may have changed dramatically or ceased to exist entirely. Communication becomes not a conversation, but a delayed record. This delay complicates the idea of contact. Even if two civilizations detect each other, meaningful interaction would be extremely slow. Responses could take generations or longer. From this perspective, the universe may not be silent because it is empty. It may be silent because its inhabitants are not synchronized. This lack of synchronization is reinforced by the sheer number of variables involved. Planet formation times differ. Biological evolution proceeds at different rates. Environmental disruptions can reset progress without warning. A planet may host life for billions of years without ever producing intelligence. Another may produce intelligence briefly and then lose it. These timelines do not align neatly. When we imagine extraterrestrial civilizations, we often imagine them as stable and enduring. In reality, stability may be rare. Complex systems tend to be fragile, especially over long periods. The idea that civilizations might not coincide in time offers a simple explanation for the silence we observe. It does not require life to be rare. It does not require intelligence to be impossible. It only requires that civilizations be temporary. This perspective shifts the question slightly. Instead of asking where everyone is, we might ask when they were or when they will be. In the next part, we will explore this idea further. We will look at how cosmic timescales, stellar lifetimes, and evolutionary pacing combine to make overlap unlikely, even in a universe full of life. To understand why temporal overlap between civilizations may be rare, it helps to look at how unevenly time is distributed across the universe. Not all stars formed at the same moment, and not all planetary systems evolve at the same pace. Stars are born continuously over billions of years. Some of the stars we see today formed shortly after the galaxy itself began to take shape. Others are relatively young, having formed only a few 100 million years ago. This difference alone creates enormous variation in the potential timelines for life. Massive stars live fast and die young. They burn their fuel quickly and may explode as supernovae after only a few million years. Any planets orbiting such stars would have very limited windows in which life could develop. Smaller stars, by contrast, evolve much more slowly. Red dwarf stars, which are the most common type in the galaxy, can remain stable for trillions of years. Planets around these stars may have vastly longer periods during which life could potentially emerge. This means that some planetary systems may not yet have reached a stage where complex life is possible. Others may have passed through that stage long ago. The concept of a habitable window extends beyond location in space. It also applies to time. A planet may be habitable only during certain periods of its history. Early in a planet's life, conditions may be too extreme. Later, geological activity may slow, magnetic fields may weaken, or atmospheres may thin. Life, if it exists, must arise and persist within these changing conditions. Earth itself provides an example of this temporal limitation. For much of its history, Earth's atmosphere lacked oxygen. Complex life could not have existed under those conditions. Only after a long sequence of biological and geological changes did the planet become suitable for large organisms. Even then, intelligence appeared late. This suggests that the window for technological civilization on Earth may be relatively narrow compared to the planet's total lifespan. If this pattern holds elsewhere, then many planets may host life without ever producing technology. Others may briefly produce technology before conditions change again. Another factor is cosmic environment. Regions of the galaxy experience different levels of radiation, stellar density, and gravitational disturbance. Stars closer to the galactic center may be exposed to more frequent supernovae and higher radiation levels. These events can disrupt planetary environments and slow biological progress. Stars in quieter regions may offer more stable conditions, but stability alone does not guarantee rapid evolution. Evolution depends on both opportunity and pressure. Too much disruption prevents complexity. Too little may slow innovation. Time also interacts with chance. Major evolutionary transitions on Earth appear to have depended on rare events. Endosymbiosis, which led to complex cells, may have occurred only once. Mass extinctions reshaped life's trajectory in unpredictable ways. If such events are rare, then the timeline of intelligence may be highly sensitive to random factors. Two planets with similar starting conditions could diverge dramatically over billions of years. This sensitivity makes synchronization unlikely. Civilizations may emerge at different times, separated by millions or even billions of years. Even if civilizations exist simultaneously, they may still miss each other. Detection depends on alignment in time, space, and behavior. Signals must be produced, travel across space, and be received during overlapping technological phases. This creates a narrow corridor of possibility. Outside that corridor, civilizations remain effectively invisible to one another. Some researchers describe this as a problem of temporal bandwidth. The universe may host many civilizations across its history, but only a few at any given moment. At any snapshot in time, the galaxy could appear silent. This view changes how we interpret the absence of evidence. Silence does not necessarily imply rarity. It may simply reflect the difficulty of coincidence. As our observational tools improve, we may begin to sample a larger portion of this temporal space. We may detect older remnants, subtle anomalies, or long-lasting signatures that persist beyond the lifespan of civilizations. For now, our observations are limited to a brief moment in cosmic history. We are listening during a narrow slice of time, using methods that favor certain types of signals. Understanding this helps place the silence in context. It becomes less surprising and more informative. In a universe shaped by long timescales and uneven evolution, overlap is not guaranteed. Civilizations may exist, but not alongside us. They may belong to the past, or they may belong to a future far beyond our reach. When scientists search for life beyond Earth, they are not searching blindly. They use specific tools, methods, and assumptions. These choices shape what can be detected, and just as importantly, what remains invisible. One of the most important limits is technological. Our instruments, while advanced by human standards, can observe only a small fraction of the universe in detail. Most exoplanets are detected indirectly, through changes in starlight or motion. Their surfaces, oceans, and potential ecosystems remain hidden. Even when studying atmospheres, the signals involved are extremely weak. A planet's atmosphere contributes only a tiny modification to the light of its star. Detecting this requires long observation times and favorable alignments. As a result, only a small subset of known exoplanets can currently be studied this way. Another limitation is distance. The farther a planet or civilization is, the harder it is to detect any signal from it. Signals weaken as they travel, spreading out and blending into background noise. At interstellar distances, even powerful transmissions can become indistinguishable from natural sources. Time further complicates detection. We are observing the universe as it was, not as it is. Light from distant objects may have traveled for thousands or millions of years. Any signal we receive today represents a snapshot of the past. This means that even if a civilization existed, its detectable phase may have ended long before its signals reached us. Detection depends not only on existence, but on timing. There is also the question of what kinds of signals we are prepared to recognize. Most searches for extraterrestrial intelligence have focused on narrowband radio signals. These signals are chosen because they are unlikely to be produced by natural astrophysical processes. However, this approach assumes that other civilizations use technologies similar to our own. It assumes they choose to communicate intentionally, or that their technology leaks energy into space. These assumptions may not hold. Advanced civilizations could use communication methods that produce little detectable radiation. They may rely on tightly focused transmissions, optical signals, or entirely different physical principles. Human perspective also introduces bias. We tend to search for life that resembles life on Earth. We look for familiar molecules, familiar temperatures, and familiar environments. This approach is practical, but it is also limiting. Life elsewhere may not rely on the same chemistry. It may operate at different temperatures, pressures, or energy scales. Such life could remain invisible to our current detection strategies. Another bias comes from our expectations about intelligence. We often equate intelligence with technology, and technology with large-scale modification of the environment. Yet intelligence does not necessarily lead to expansion, communication, or detectable artifacts. On Earth, many intelligent species exist without altering the planet in ways visible from space. Even human technological activity became detectable only recently, and even then, only weakly. Some researchers suggest that civilizations may deliberately minimize their external footprint. Efficiency, sustainability, or caution could all lead to reduced detectability over time. There is also the problem of interpretation. The universe produces many signals that initially appear artificial. Pulsars, quasars, and fast radio bursts were all once mysterious. In each case, further study revealed natural explanations. This history encourages caution. Unusual signals require rigorous verification. False positives can mislead and delay understanding. At the same time, false negatives are equally possible. Signals may exist that we do not recognize as significant. Patterns may be present that do not match our expectations. Our detection strategies are shaped by what we already know. They are effective within those boundaries, but blind beyond them. As a result, the absence of detected life does not necessarily indicate absence of life itself. It may reflect the narrow window through which we are currently observing the universe. In the next part, we will explore how these limitations interact with human assumptions. We will examine how the questions we ask influence the answers we are able to find, and how expanding our perspective may change the search itself. Beyond technological limits, one of the strongest constraints in the search for life is human perspective itself. The way we frame questions influences what kinds of answers we are able to recognize. Humans naturally interpret the universe through familiar patterns. We understand life based on the only example we know in detail, Earth. This makes our search practical, but it also introduces assumptions that may not apply elsewhere. One major assumption is that life must resemble terrestrial biology. We often look for carbon-based chemistry, liquid water, and Earth-like temperatures. While these conditions are reasonable starting points, they may represent only one of many possible pathways. Life elsewhere could rely on different solvents, such as liquid methane or ammonia. It could operate at temperatures far below freezing or far above boiling. Such forms of life might not produce chemical signatures we know how to identify. Another assumption concerns metabolism and energy use. On Earth, life exploits chemical gradients and sunlight. Elsewhere, life might rely on geothermal energy, radiation, or processes unfamiliar to us. These energy sources could leave subtle or indirect traces. Anthropocentrism also affects how we think about intelligence. We often assume that intelligence leads to communication, expansion, or technological modification of the environment. However, intelligence does not necessarily require outward expression. An intelligent species could remain localized, conservative in resource use, or uninterested in signaling. Its technological footprint might be small enough to escape detection even at relatively close distances. Human history itself demonstrates how recent our detectable phase is. For most of our existence, Earth would not have appeared inhabited to distant observers. Only in the last century did artificial radio emissions become detectable, and even those signals are weak and fading. This suggests that detectability is not a stable trait. It is a transient property that depends on technology, behavior, and choices. Another bias arises from how we interpret anomalies. When unusual signals are detected, scientists are trained to favor natural explanations. This approach is methodologically sound, but it can delay recognition of genuinely novel phenomena. At the same time, it protects against premature conclusions. The balance between skepticism and openness is difficult to maintain. There is also the issue of scale. Human perception evolved to function at biological and planetary scales. We are less intuitive when dealing with cosmic distances, deep time, and extreme energies. As a result, we may underestimate how diluted or subtle evidence becomes over interstellar distances. What seems obvious at close range may vanish entirely when spread across light years of space. Some researchers argue that we may already be surrounded by indirect evidence, but lack the conceptual tools to recognize it. Technological activity could alter stellar light in ways we do not yet understand. Civilizations might manipulate matter or energy in forms indistinguishable from natural processes. Even large-scale engineering, if designed efficiently, might blend into astrophysical background noise. Without knowing what to look for, such signatures would be easy to miss. Language and expectation also shape interpretation. Terms like signal, artifact, or message imply intent and design. Life elsewhere may not produce anything that fits these categories. Another limitation comes from how research is prioritized. Search strategies often focus on what is measurable with current instruments. This reinforces existing assumptions and narrows the scope of inquiry. Expanding the search requires new models, new questions, and new ways of thinking. It also requires patience, because progress may be slow and ambiguous. Understanding these limitations does not weaken the scientific search. It strengthens it. By recognizing biases, researchers can design broader and more flexible strategies. The absence of detection, when viewed through this lens, becomes less definitive. It reflects the current boundaries of knowledge rather than final conclusions. As our understanding grows, so too will our ability to imagine unfamiliar forms of life and intelligence. With that expansion may come new methods of detection and interpretation. For now, it is important to remember that the universe does not owe us clarity. It operates according to principles that may not align with human expectations. The search for life is not only about discovering others. It is also about learning the limits of our own perspective. In the final theme of this exploration, we will reflect on what this long search has already changed about humanity, how it reshapes our understanding of our place in the universe, regardless of whether we ever find definitive answers. The search for life beyond Earth has not yet provided a definitive answer. However, it has already changed humanity in measurable and lasting ways. One of the most important changes is how we understand our place in the universe. Before modern astronomy, Earth was often viewed as central, unique, and isolated. The discovery of exoplanets fundamentally altered this view. We now know that planets are common. They form naturally around stars throughout the galaxy. Earth is no longer seen as a rare anomaly, but as one example among many possible planetary outcomes. This shift has influenced how scientists think about habitability. Instead of asking whether Earth is special, researchers now ask which conditions matter most. They examine factors such as atmospheric stability, geological activity, and stellar behavior. The search has also changed how we define life. Life is no longer thought of only in terms of animals, plants, or intelligence. It is increasingly understood as a chemical and physical process that can take many forms. This broader definition has expanded scientific inquiry. Fields such as astrobiology now combine biology, chemistry, geology, and astronomy. Questions about life are no longer confined to a single discipline. Another significant change involves how we think about intelligence. The absence of detected civilizations has encouraged scientists to reconsider assumptions. Intelligence may not be common. It may not be stable. It may not lead to long-term technological societies. This realization has influenced research into evolution and behavior on Earth. It highlights how contingent our own development may have been. Small changes in history could have led to very different outcomes. The search for extraterrestrial life has also emphasized the fragility of planetary environments. Studying other worlds has helped scientists better understand climate processes, atmospheric loss, and planetary change. Comparing Earth to other planets has clarified how unusual our balance of conditions is. Liquid water, plate tectonics, a protective magnetic field, and a stable climate have all contributed to Earth's long habitability. This comparison has reinforced the importance of planetary stewardship. While the search for life looks outward, it has also deepened concern for the only inhabited world we know. The search has changed how scientists approach uncertainty. In many areas of science, progress comes through clear answers. In astrobiology, progress often comes through narrowing possibilities rather than confirming conclusions. Learning to work within uncertainty has refined scientific methods. Researchers develop models that account for incomplete data and competing explanations. This approach has broader implications beyond astronomy. It influences how science addresses complex systems, from climate to ecosystems. The search for life has also reshaped technological development. Instruments designed to detect faint signals have driven advances in optics, sensors, and data analysis. These technologies often find applications beyond astronomy. At the same time, the absence of discovery has encouraged patience. Large scientific questions may take generations to answer. Not every effort produces immediate results. This long-term perspective contrasts with the pace of modern society. It reminds us that some questions are not meant to be resolved quickly. The search has also influenced public imagination. While science fiction often dramatizes contact, Scientific inquiry emphasizes probability, limitation, and scale. This difference has helped separate scientific curiosity from expectation. Finding life is no longer assumed to be inevitable or imminent. Instead, the search has become a way of learning about the universe itself. Each discovery, even when it does not involve life, adds to a growing picture of cosmic diversity. In this sense, the search has already succeeded. It has expanded knowledge, refined methods, and reshaped understanding. In the next part, we will look more closely at how this search affects humanity on a deeper level. We will consider how it changes our sense of identity, responsibility, and long-term perspective. Beyond its impact on science and technology, the search for life beyond Earth has gradually reshaped how humanity understands itself. This change has been subtle, unfolding over decades rather than moments, but it is profound. One of the most important shifts is the way we think about uniqueness. For much of history, humans assumed that intelligence, culture, and technology were central features of the universe. Modern astronomy has challenged this assumption. We now understand that the universe does not revolve around complexity. Most of it is simple, quiet, and governed by long-term physical processes. Complex life appears to be an exception rather than a rule. This realization encourages humility. It suggests that intelligence may not be a guaranteed outcome of evolution, but a rare convergence of conditions. Our existence may depend on a long chain of events, any one of which could have unfolded differently. The search for life has also altered how we think about permanence. Civilizations, like species and planets, may be temporary. They arise under specific conditions and persist only as long as those conditions remain stable. This perspective places human history in context. Our technologies, institutions, and cultures are recent developments on a cosmic scale. They are not fixed features of the universe, but fragile arrangements. Recognizing this fragility has implications for how we view responsibility. If intelligent life is rare or short-lived, then preserving it becomes more significant. The search for life elsewhere indirectly highlights the value of life here. Studying other planets has reinforced this idea. We see worlds that lost their atmospheres, became uninhabitable, or never developed stable conditions. Earth's long-term habitability now appears less accidental and more delicate. This understanding influences how scientists and thinkers approach planetary care. Climate stability, biodiversity, and environmental balance are not abstract concerns. They are factors that determine whether a planet remains suitable for complex life. The search has also changed how humanity thinks about meaning. In the absence of confirmed extraterrestrial civilizations, meaning is not derived from cosmic companionship. Instead, it emerges from awareness and choice. We may be alone in our galaxy at this moment, or we may not. Either possibility carries weight. If we are alone, then intelligence is rare and worth preserving. If we are not, then intelligence is part of a broader cosmic story. In both cases, the responsibility remains local. How we treat our planet, our technology, and each other matters regardless of what exists elsewhere. The search for life has also expanded our sense of time. It reminds us that progress is not measured only in years or generations. Some questions unfold over centuries or millennia. This long-term perspective contrasts with the urgency of everyday life. It encourages patience and restraint. Not every question requires an immediate answer. In science, the absence of a final conclusion does not signal failure. It signals that inquiry is ongoing. The search itself becomes a way of learning. As instruments improve and knowledge expands, future generations may detect signs we cannot. They may reinterpret data we have already collected, or they may continue listening in silence. The outcome is uncertain. What is certain is that the search has already changed how humanity sees the universe. It has replaced centrality with context, certainty with probability, expectation with careful observation. In this way, the question, "Are we alone?" becomes less about finding others and more about understanding ourselves. It invites us to consider how rare awareness might be, how fragile complexity can be, and how meaningful even a small corner of the universe can become when it is capable of reflection. As we reach the end of this exploration, it is important to return to where we began, not with an answer, but with a question. The universe remains vast, quiet, and largely unknown. It does not rush to explain itself. It unfolds slowly, over timescales that extend far beyond human experience. Whether life exists elsewhere or not, the search has already given us something valuable: perspective, patience, and a deeper understanding of how unusual awareness itself may be. You do not need to carry these ideas forward consciously. They do not ask for resolution. They are meant to rest gently in the background, like distant stars. The universe does not require us to understand it fully. It simply exists. And for now, that is enough. If you made it this far, thank you for being here. If this helped you relax, consider leaving a like and subscribing. I'll keep making more content like this.